Instrumental variables, or IV, offers a powerful solution to endogeneity. This video provides a complete guide with real examples on how to use IV to achieve unbiased causal inference. We are solving the problem of endogeneity. When an explanatory variable, x, is correlated with the error term, your regression coefficients are biased and untrustworthy. Since you can't always run a randomized experiment, IV uses a helper variable, z, to isolate the clean, unbiased relationship between x and y. An instrumental variable, z, affects your variable of interest, x, but does not directly affect the outcome, y. This means z affects y only through x. This key insight allows us to use the variation in x created by z to get clean, unbiased estimates. Consider the question: does IT training increase employee productivity? The problem is that smarter employees are selected for training and are naturally more productive. This makes x, training hours, endogenous. Our IV solution uses the distance from home to the training center as z. Closer employees attend more training, but distance itself does not affect productivity, except through training. A valid instrument must satisfy two requirements. First, relevance z must significantly affect x. We test this by ensuring the F statistic is greater than 10 in the first stage regression. Second, the exclusion restriction z must affect y only through x, with no direct effect on y. This condition cannot be statistically tested, requiring theoretical arguments and domain knowledge. Let's test relevance with our example. The first stage regression shows that each extra mile from the center reduces training by 1.5 hours. With an F statistic of 45.2, which is much greater than 10, the relevance requirement is strongly satisfied. Distance is a strong predictor of training hours. The exclusion restriction is the critical part. We only allow z to affect y indirectly through x. Direct effects, where z affects y directly, are not allowed. For example, does distance to the training center directly affect productivity? Potential violations, like stress from long commutes, must be considered carefully. The magic of IV lies in separating the variation in x. OLS uses all variation, both the contaminated variation correlated with the error term and the clean variation. IV uses only the clean variation that comes from the instrument, which is not correlated with the error term. This results in unbiased coefficients. Instrumental variables are implemented using two-stage least squares, or 2SLS. Stage 1 predicts x using z, generating x hat, the clean part of x. Stage 2 uses this predicted x hat to explain y. The resulting coefficient is the unbiased IV estimate because it uses only the clean variation derived from z. In the numerical example, OLS cannot distinguish if higher productivity is due to training or pre-existing high ability. The IV solution first predicts training using only distance, ignoring ability. Then, it uses these predicted values in stage 2 to estimate the true effect of training on productivity. In a real-world example, we ask if CRM software increases sales revenue. The problem is that high-performing teams adopt CRM first. Using promotional pricing timing as the instrument, IV estimated an increase of $120,000, while OLS overestimated the effect at $250,000, demonstrating the bias of OLS. There are three main tests for your instrument. The first stage F test ensures relevance, requiring an F statistic greater than 10. The over-identification test, like the Sargan/Hansen-J test, checks if multiple instruments are consistent. Finally, the exclusion restriction relies on theoretical arguments, as it cannot be statistically tested. Avoid common IV mistakes. Do not use a weak instrument, where the F statistic is below 10. Ensure the exclusion restriction is not violated, meaning z does not directly affect y. Be mindful of small sample sizes, as IV requires more data. Finally, remember that IV estimates the local average treatment effect, or LATE, for the population influenced by the instrument. Use IV when you have endogeneity, cannot run an experiment, and have a valid, relevant instrument with a large enough sample size. Do not use IV if you can run a randomized experiment, the instrument is weak, or simple controls would suffice. When choosing an approach, IV fixes all types of endogeneity but requires a valid instrument. Alternatives include fixed effects for panel data, diff and diff for natural experiments, or matching for selection on observables. Experiments remain the gold standard when randomization is possible. Strategies for finding instruments include looking for natural experiments, such as policy changes or geographic variation, and timing variation, like staggered policy rollouts. Other sources are decision-maker characteristics and historical accidents, such as the legacy of past policies. Key takeaways: IV solves endogeneity using the instrument's clean variation. It requires testable relevance and a plausible exclusion restriction. 2SLS is the implementation method. Test relevance with an F statistic above 10, but remember that good instruments are rare, and IV estimates the local average treatment effect. IV is like using a clean water source. It filters out contaminated variation to give you a pure, unbiased effect. Mastering IV allows you to unlock causal inference, even when running experiments is impossible.